Welcome to the Webster CyberLab. This is a discussion about man-in-the-middle attacks for the Laboratory on Man-in-the-Middle Attacks. I'm Fred Cohen, the CyberLab director, and joining us today is Garrett G., one of the CyberLab managers. Generally, when we talk about the CyberLab, we're talking about the science of cybersecurity. Today, we're going to talk about man-in-the-middle attacks, but the outline is the same. The science of cybersecurity is based on causality, testability, refutation, and adaptation. In essence, cause works via mechanism to produce effects. It's shown by the equation C implies through mechanism M, E. And this causality notion is the foundation of all science. If you're going to have a scientific theory, it has to be testable by experiment. That is to say, you have to be able to have an experiment that if it came out one way, would show that the theory is wrong. And if it comes out the other way, well, it confirms the theory, but it doesn't prove it right. For a universal theory, that is a theory about an infinite number of different things, you can't prove the theory right. No experiment can prove the theory to be right. If the experiment demonstrates that the theory is wrong, then the theory is wrong, but no matter how many times you get it right, there might be some other case that shows up later on that you weren't aware of. So to test anything scientifically, we need to be able to measure something. And one of the questions in cybersecurity is, what do we measure? And so without the theory of cause, mechanism, and effect, we really don't know what to measure. Once we have the theory, we can measure the cause, the mechanism, and the effect, and try to measure what else is going on in the environment to differentiate the hypothesized causality from everything else. When a theory is refuted, of course, we might adapt the theory, or we might just try something else, might abandon it. A good example of a scientific theory is the flat Earth theory. This was a theory from long ago. Basically, the theory was that the Earth is flat. It turns out an experiment proved it wrong. That experiment was circumnavigation of the globe. But before then, it wasn't really refuted. And after that, science developed a new theory. Well, the Earth's a big ball. And over time, we've adapted that theory. I should note that if you're building buildings, the scientific theory that the Earth is flat is good enough. I mean, essentially, nobody building buildings compensates for the curvature of the Earth. It would have to be an awfully big building to make that sort of difference. And maybe for some scientific experiment buildings, that makes a difference because they're trying to get extremely tight tolerances. But for the most part, the flat Earth assumption is good for building houses. Here's a theory of man-in-the-middle attacks. The theory is that if you respond fast enough, you can get in the middle of the protocol. That is, a protocol is an exchange of information between two or more parties. In this case, computers is a good example. And the idea here is that the first legitimate seeming protocol response wins. So if you send out a message and I respond before the legitimate place with something that seems right, then you'll probably believe it. So more specifically, when the internet requests are made, the first syntactically correct response will be treated as if it was right, even if it's not actually right, whatever right means. The mechanism is that you beat the legitimate protocol response. The forged, or in this case, the first one back, even though it's not the real one, whatever that means, is trusted. And here's a picture that shows it. You have the green computer sending out a request for whatever purpose, and it gets a response back from the evil red server first, and it believes it, so it starts communicating with the red server, and then the red server can go communicate with the other server and act as a man in the middle. That is, it intercepts and intervenes between the communication. And that's the effect, is that you can redirect the protocol through you. Essentially, you become the man in the middle, even if you're not physically in the middle between the other computers. And here are some examples of winning the race that we're going to use in our experiments. One of them is ARP responses to get MAC addresses. So ARP is the address resolution protocol. It's used to resolve addresses, MAC addresses, the hardware address of an Ethernet card, for example, to an Internet Protocol address or IP address. And so what happens is, on a local area network, for example, if I'm communicating, I will tell the recipient that it's for them, their Ethernet card rather than any other Ethernet card, by including the MAC address in the low level, level 1. It's typically called a protocol, or maybe it's layer 2. So if I can convince the other computer to send the wrong MAC address, then the legitimate computer won't hear it. My computer will hear it, and then I can respond to it directly, and then I can also communicate with the other machine using its MAC address, and that effectively puts me in the middle. The second example is DNS, or domain name service or system. And in this case, if we can respond to a request for a domain name service, we can send back an answer to a request for a name that's not legitimate. If our answer gets there before the legitimate response, maybe saying that it's no good or something like that, then we'll be able to cause the website or wherever else you're going to come through us or to us, and then we can send it on if we care to do that, making a man-in-the-middle attack again. So to test the theory, what we want to do is isolate a specific protocol element one at a time. So we want to do either the ARP or the DNS or whatever protocol we want to test it on. We want to limit the environment to only the relevant protocols and systems. The idea here is to get rid of other things that might affect the experiment so that we can differentiate the things we're looking for, the cause, mechanism, and effect, from other things. We then measure the protocol response times and frequencies. Remember, the theory is that the fastest one wins. So in order to figure out which one's actually fastest, we have to measure it. So a good approach to this might be to make an adjustable forgery so that we can change the response times from faster than the legitimate response times to slower. And then you make an adjustable forgery. You measure legitimate and forgery response times, predict the winner based on which is fastest, then do a repeated set of experiments adjusting the forgery speed. Test over the range of speeds from slower than the legitimate to similar speeds to faster. Maybe we'll find that you have to be a lot faster, or maybe just a little bit faster, or maybe if you're a little bit slower but still in time, maybe you win, who knows. See if the theory is confirmed or refuted, and then examine confounding factors and other causes and mechanisms, especially if the experiment surprises you, which it often might. So here's the man-in-the-middle experiment. The protocol is ARP. The cause is ARPs from a forger beating legitimate ARP responses. The mechanism is that it sets the MAC address of the legitimate internet protocol to the forged MAC address so that the datagrams are sent to the wrong physical machine. And then the effect is that the protocols use the forged MAC address for the legitimate IP and send the datagrams the wrong way. Now I'm going to hand it over to Garrett in the CyberLab. Take it away.
Hello, everyone. I have 3 windows open. The first one is on the top is our client browser window. Its IP address is 10.0.0.146. On the lower left, we have the attacker, and that is at 10.0.0.142. We also have a web server at 10.0.0.205. And the web server is just serving up a very basic web page. There's the source content, and we will just quickly browse to that in its normal operation. So a very basic web page, hello world is its title, image, and some sample text down below. So for this man-in-the-middle demonstration, we are going to utilize EtterCap and show the filter. And then from here, we are going to run that code going after the client, which is at 146, and specifically against the server 205. So we'll run that. And if we hit refresh on the browser, you'll notice that the title has changed, the image was inserted, and also some text was inserted. And this is just a very basic demonstration, very visible demonstration of injection of content where a malicious person will be more stealth and potentially inserting malicious JavaScript instead of just adding random images. So we will stop that attack. And just to make sure that nothing else is going wrong, we'll refresh the page and it is back to normal. And that is it for this man-in-the-middle demonstration.
Thank you. Thank you, Garrett. So let's interpret the experiment. The measured phenomena is the response results displayed by the browser. We saw the responses, and it seems like it's obvious that when the forgery is turned on, the responses are different from when it's not turned on. So the controlled variables was the forged responses, either on or off. The experimental outcomes, well, it's normal operation without the forgeries. A different operation with the forgeries, they were doing something. We didn't particularly find a way to subtract out the experimental overhead. So there might be side effects we're unaware of. And then, there's another interesting question. Is there a defense? And let me just give you some ideas here. Maybe if the legitimate was faster, it would win, and that'd be a defense. Another one would be, maybe we need to make a smarter infrastructure so we can tell the difference between, the faster and the slower, or the forged and the real, whatever that means. Or maybe a smarter browser, or a smarter supporting system that the browser runs on. So I'm not going to answer the questions. I'm instead going to move on to the other man-in-the-middle experiment. This one's a DNS protocol. The cause here is that DNS responses from the forger beat the legitimate DNS, or this is the theory. The mechanism is that the forgery mechanism listens for DNS requests and forges the responses. That is, it responds faster than some other machine, giving the answers. And we'll call that a forgery because it's first, and we think if we don't do this, it's not legitimate. The effect is that the protocols use the forged IP address, not the legitimate IP address. So again, take it away, Garrett.
Hello, everyone. So on the top screen, we have a browsing machine. It's at 10.0.0.146. You could see here that it's configured for the DNS server at 10.0.0.205, and that is our DNS and web server. So 10.0.0.205. The attacking machine is going to be at 10.0.0.142. And just to show that DNS is going to that 205 machine, if we just do something ridiculous like looking up a non-existent record like that, it kind of responds, but it's essentially that does not exist. So on the attacking machine, we will look at its configuration file, and essentially we have a record that says for anything, resolve it to this IP address. So as we run that code, if we do this exact same lookup to that exact same server, the DNS record will actually be spoofed from 205, and it's actually now resolving. So in theory, if we just go to that domain, or anything really, it'll actually be redirected to that same web server that we had before. So no matter what we put in here, we could just put in random content, and it will be resolved to that same IP address because it's being spoofed from DNS in the middle. And once we turn it off, we will see that, once again, it doesn't resolve, and going to this funny domain does not really go anywhere. And that is it for this demo. Thanks.
Thank you again. So the measured phenomena, again, is response results displayed by the browser. The control variables are forged responses either on or off. The experimental outcomes, well, you get normal operation without forgeries, different operation with forgeries, whatever that means. Again, we didn't do anything to subtract experimental overhead. And we have the same questions about the possibility for defense. So here's the lab assignment. What we want you to do is a better job of measuring and testing. The theory says that the first legitimate seeming response wins, right? So the problem here is that the times for the forged responses were not varied. The times were not measured. None of the times were measured. So what we want you to do is find a way to measure these times and vary, especially the forgery time, which is easy to vary. and test it repeatedly, varying those times. And then figure out whether it's really the first one that wins, whether it's really time that's the mechanism here, or maybe it's not. And if it's not, then what's going on here? But before you just go off and test, we want you to create a predictive equation. We want your equation to tell us how timing makes a difference, predict the performance as a function of timing, that is what the outcome of the experiment is going to be depending on the timing, do tests to confirm or refute the validity of your equations. So we want you to do tests, and we want the test to demonstrate, either confirm your hypothesized theory or refute it. And if it refutes it, the theory's wrong. We want you to report the results. So that's the first part. Part two is, what about defenses? And here's an example. And I'm not telling you to use this defense. I'm just throwing up an example. Suppose we use cryptography like SSL between the browser and the server. And you're welcome to try this if you want. Will this work? And in which cases will it work? Will it work for both of these forgery mechanisms, or only for one of them, or for neither? We want you to create a theory about encryption changing the situation. That is, we want you to identify cause, mechanism, and effect, and how the defense changes the cause, mechanism, or effect. And, what's the cause, mechanism, and effect of the defense, and how does that interrupt the cause, mechanism, and or effect of the offense? And we want a predictive equation for the relevant parameters, whatever they are. Since you make up the equation, you have to tell us what the parameters are and generate a predictive equation. And then you want to do experiments. We want you to design test cases for each of the man-in-the-middle methods, identify experimental overhead and measurement limits, and perform the tests and write up the results. So that's the lab assignment. I'm just going to continue on and talk a little bit about CyberLab and its use. It's for science. And science requires that we isolate the phenomena under study. And that means minimize the co-founding or confounding factors. Repeatable, we want it to be repeatable within defined bounds. So that means you have to be able to do the same thing again and again and expect to get the same answer within the defined bounds of the measurement. So there's measurement error and other errors associated with the limits of the environment. So it has to be repeatable within defined bounds, and we certainly want you to tell us what the defined bounds are and why. And then consistently measurable regardless of the measurer. So when you devise an experiment, somebody else should be able to repeat your experiment following your instructions and hopefully get the same answer within the defined bounds. If you say there's an area where it's unclear and this area it is clear, then they should find the same thing. It's important to note that this simplification that we're doing allows us to examine the theories and think of it as, the theory of a building and how it works versus a beam and how it works. You can do all sorts of experiments, bending a beam, twisting a beam, seeing where it breaks, how much load it takes. But you can't really do that very much on a building, because once you break it, you got to build a new building, and it's pretty darn expensive and time consuming. And there's so many things going on in the building compared to a beam that you may never differentiate one thing from another. Engineering, of course, is far more complicated. It applies scientific results in a real complex world, the reality. And generally, it seeks to create rules and calculation methods that allow you to make reasonable decisions. And I talk about these defined bounds. Usually engineering defines things so that there's some slop. So it's not exactly perfect, but if it goes wrong a little bit, we have enough extra, so we'll still be safe. But we need the science to do the engineering. And we also, of course, need the engineering if things are going to work in the real world. So if the theory is reasonably good, we can alter the times, for example, make the server faster, the forger slower, change the threshold point for man-in-the-middle attack. That should work. Another one, we should be able to change the protocols or mechanisms. For example, adding cryptography, if that works. Making Ethernets, have fixed MAC addresses, that might work. Or something else that you come up with. Science is wonderful because people get to do different things than the other people did before them and find new things out. We can identify and predict breaking points and times, which means from a standpoint of engineering, we can create specifications that say, well, this will work under these conditions, but it won't work under those conditions, or it'll be subject to failure under those conditions. And then the person that wants to use it can decide whether they want to be subject to that kind of failure. And of course, we can test these approaches within the CyberLab by doing controlled experiments for each method combination, methods individually and combinations of methods within the limits of time and resources. And we can measure effectiveness over engineered ranges by varying these parameters. So if the theories are good, the results will meet the predictions, and if not, well, we probably need to refine the theory and retry. So that's the end of the formal presentation for the people that are present. I'm going to engage in discussions. I'm going to turn off the recording, and thank you for attending.